In this video, we're going to be looking at some important ideas like restrictions to domain, rational functions, and equivalent functions. This is the first lesson of Unit 2, Function Transformations, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website tutor.ca and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to Lesson 8 in the Second Teacher Program's course on Grade 11 Functions. Here we're going to be taking a look at similar content to Section 2.1 from the textbook. We're beginning Chapter 2, and we are starting with rational functions and restrictions. So those are our main topics for today. Let's go through a little outline of, that's my notes, let's go through a little outline of everything that we're going to discuss today. So to begin, we are going to review domain. Okay, we're going to talk about restrictions. If I could spell, that'd be nice. So restrictions. And then after that, we are going to talk about equivalent functions. Okay, we're going to talk about rational functions, which is part of the name of the chapter here, right? And then we're going to be exploring some, we're going through a lot of examples and exploring through all this through like a lot of different examples. And so the final thing that we're going to talk about is just how to simplify a rational function. Okay, and this last step actually brings us to our next lesson. So lesson 9 will continue this idea. Okay, so simplifying rational functions, we'll talk about that at the end. But then if you're confused about that last bit there at the end, if the last thing we're talking about doesn't make sense, like maybe there's a lot to go through there, it's because there's a whole other lesson that's going to cover just this concept, but we're going to start here with it, and we'll remember that for the next lesson. So to begin, let's talk about the domain of a function. So let me remind you quickly what our definition was. So the domain, start a new line here. So the domain of a function is the set of all x values you can put into a function and actually get an output. So to kind of refresh what we mean by a domain, I'm going to give us 3 examples here. F of x equals x squared. G of x equals the square root of x. And h of x equals, it was 2x plus 1 over x. So we're going to look at the domain of each of these functions. Okay, we're going to look at the domain of each of them and try to understand why it is what it is. So we have to ask ourselves, what values of x can I put into this function and actually get an output out of it? Right? Or in other words, what values of x can I square? Well, I can square x regardless of what value it is. I can always square a number, right? 2 I can square. 0 I can square. -2 I can square. A fraction I can square. A negative fraction I can square. I can square everything, right? And similarly, if we look at the graph of y equals f of x, it would look something like this. Right? Of y equals x squared, we would have something like this. If that's our x-axis, that's our y-axis, then we would have something like that, right? That's our basic parabola, x squared. And you can see that for every x value, there is a corresponding y value, corresponding point height above the graph, height above the x-axis that we get our f of x, right? So we can see that for every x value that exists, and so the domain here is all real numbers. So the domain is x is an element of all real numbers. And that's it, right? X is an element of all real numbers. X can be any number. So that's the domain of our function. Those are all the x values that we can possibly put into the function. Okay, that's the first example. Let's look at our next example. G of x equals the square root of x. So what numbers can I take the square root of? Well, I can take the square root of positive numbers. So first of all, square root of 4 equals 2. Square root of 2 equals, well, some decimal number, but it is possible. There is the square root of 2. That's a number that exists, so that's fine. Square root of a fraction, totally fine too. Square root of a half, right? Or maybe I'll say square root of a quarter is a half, right? Because a half squared is a quarter. and so on. I mean, we could do that. The thing is, what about -2? Square root of -2. What number squared gives me -2? Ah, we have a problem. You cannot take the square root of negative numbers when you're just talking about the real numbers, right? So there is no answer there's no real number answer for this thing right here. So it doesn't make sense for us to put a negative number into the function. If I look at the graph of this function, it would look something like this. So if I just sketch it out here quickly, there's our x-axis, there's our y-axis. If I were to sketch out this function, it would look something like that. So notice, for all the positive x values, there is a corresponding f of x value. There's a corresponding height, or a y value, above the graph. But for all of the negative x values, well, I'll never touch the graph if I go anywhere here, right? The graph just doesn't exist there, because there is no square root of any of these negative x values, right? So the domain of this function, should be clear actually, maybe for this one. So the domain I'm going to highlight in blue. So that's the domain. The domain of this function is going to be just the positive numbers, right? So that goes infinitely like that, infinitely in either direction there, right? So that's the domain. I'm going to make this a little bit smaller because I realize I'm going into the territory of this next example here. So just so I have the space. But yeah, that's the idea. That's going to be our domain. So to write that out, our domain is all real numbers, but there's a condition such that x has to be greater than or equal to 0, right? It has to be positive. We have to be bigger than or equal to 0. Okay, so there's our g of x. Now let's take a look at h of x. What about this? So what numbers can I put in here? What numbers can I multiply by 2, add 1 to, and then divide by x, right? Divide by x here. What numbers does that work for? Well, if I take a look here, right, we can see, well, if I, let's say h of 2. H of 2 would be, 4 plus 1, or I'll be more clear here, 2 times 2 plus 1 over 2, right, which would be 5/2. That's fine, right? Hopefully you can see that. I'm realizing maybe now it's covering it. I realized the function's kind of being covered here. So just I'm going to write that on the side, 2x plus 1 over x. There you go. You can see it better now. So 2x plus 1 over x is our h of x. And so h of 2 is that. H of -2, can I also take, negative numbers? Yep. So 2 times -2 plus 1 over -2. Well, that would just be -4. So -3 over, -3 over -2, or just 3/2, right? But what about 0? So h of 0 is going to be 2 times 0 plus 1 over over 0, right? Because 2x plus 1 over x, so I just replace the x with 0. And, well, this would be 1 over 0. The problem is 1 over 0 doesn't exist. The number 1 over 0 doesn't exist. You can't divide by 0, right? So 0 is not in the domain of this function, but it's just 0. So if you were to take a look at the graph, I mean, the graph is a little bit complicated, so don't worry too much about how the graph looks like this. How about we actually take a look here? So, sorry, I should have had Desmos open already. There you go. So if I take a look at the graph here, f of x, or whatever, I said g of x or h of x, but that's fine. 2x plus 1 over x. It looks like this. So again, don't worry too much about why it looks like this. We're going to get into that. But it looks like this graph right here. And so, well, you see, for every x value here, right, there is a corresponding height, right? So all the positive x values have a corresponding height. For all the negative x values, they have a corresponding height. Even here, like for an x value like right there, maybe like -0.2, you can go down and you'll meet the graph somewhere. So 0.2 is -3. But for 0 itself, this line here where x equals 0, here I'm going to draw x equals 0 on here. Well, not z equals 0, sorry. X equals 0. That blue line, the graph goes up to infinity up here, right? But it never actually touches the line. It never actually touches the y-axis there, right? And here it never touches the y-axis going down either. There is no height there. It just, this goes up to infinity like that, and this goes down to negative infinity like that. Right? So we don't actually have a value for x equals 0. And again, this graph looks funny. Lots of stuff going on here. We're going to talk about that, right? We're going to talk about that when when we get to the part on this kind of stuff. So we're not quite there yet, but just as an example. And so we see that our domain is everything except 0. So the domain of this function, the domain is the set x is an element of all real numbers such that x does not equal 0. Oops, x does not equal 0. Okay, so there's our general review of what a domain is. And so I'm just going to introduce, there's a word we just never mentioned before, and it's called the restrictions. Okay. And the restrictions are the such that's. So our restrictions here, I'm going to highlight them in blue, or I guess I already used blue, so let's use yellow maybe, are this. X has to be greater than or equal to 0. That's a restriction. The domain is x is all real numbers such that x is greater than or equal to 0. And if I ask, what's the restriction on the domain? The restriction on the domain is that x has to be greater than or equal to 0. What's the restriction over here? Oh, x cannot be equal to 0. So there are two main restrictions, and I illustrated them in this point right here. There's two important restrictions that will always be there if you have something that includes these things, right? So the notable, let me see here, notable restrictions, restrictions, oh wow, I can't spell restrictions today for some reason, are one. Well, the first thing is that denominators cannot equal 0. We saw that in this third example here, right? Everything worked except whatever made the denominator 0. Because then you have a denominator of 0 and you're trying to divide by 0, and that just can't work. You're just not allowed to do that. And there's lots of reasons why you're not allowed to do that. If anyone's curious about why, feel free to book a session with me and we can have a nice long discussion about that. But so for now, you gotta just, think about it, right? Dividing by 0 doesn't make sense. You can't split something between 0 people. Right? Even if you don't split it, you're technically splitting it between yourself. You just have one person, right? So, and even if you throw the thing in the trash, you're still splitting it between one thing, the trash. You're giving it to the trash. So you cannot divide by 0, right? So that is the first restriction, is that the denominator cannot be equal to 0, ever. So whenever you see a fraction, there's always a restriction that the denominator cannot be 0. You usually don't have to worry about this, right? Because if you see 2/5, you don't even have to think about the fact that the denominator is not 0, right? Because the denominator is 5. You never even have to think about that the denominator can't be 0. But if you have something like 2 over x, x can be any number, right? X can be any number, except 0. Right? So when you start using variables, you have to account for these little details, right? These smaller details in what you're doing. Just like in the square root, you don't have to worry about the fact that you can't take the square root of negative numbers when you're just doing the square root of 4. But if you're doing the square root of x, you do have to take that into account because x is just some number that we don't know yet. And so we have to say, okay, well, it can't be a negative number if we're taking the square root of it. Okay. So there we have that. That's our first restriction, is that the denominators can't be 0. And then I already mentioned the second restriction, which is that you cannot take the square root of a negative number, which essentially means radicands. Okay, so radicand is the thing inside a square root, has to be greater than has to be greater than or equal to 0. And I'll just write that out in words. Greater than or equal to 0. Okay, so there's our two main restrictions. Denominators can't be equal to 0, and radicands, the thing inside the square root, has to be greater than or equal to 0. We saw that here. So x has to be greater than or equal to 0, and the denominator couldn't be equal to 0. Okay. Okay, so I went through this. I'm just going to check that I've done everything that I wanted to mention in this one section. So remember, restrictions are the thing in the domain that's making it not the whole real numbers. So it's the x has to be greater than or equal to 0, or x has to be not equal to 0 for the denominator. The denominator can't be equal to 0. The thing inside the square root can't be equal to 0. Okay. So we're going to dig into these restrictions quite a bit more in this section, right? So, but I just wanted to first start you off with that, definition of restrictions here and the two main restrictions that we talk about. Okay, so let's see what we've done so far. So far, we've reviewed domain and we talked about restrictions. Let's move on now to equivalent functions. Equivalent functions. So equivalent functions. So here, okay, we are looking at when are two functions equal, right? When is one function equal to another function? So first of all, I want to start talking quickly about what does it mean for two things to be equivalent. Okay, so equivalent, let me just type that out nicer, or write that out nicer. Equivalent. Okay. You see the word equal is kind of in it, right? Equal. And so two things are equivalent if they're not, you can't say that they're the same thing. Equivalent means a specific thing. So let me give an example here. How about that? We start with an example in fractions. 3 and 6/2. Right? These are definitely written differently. 3 is a symbol, 6 is a symbol, 2 is a symbol, and then as a fraction, that's a whole new symbol. But they are equivalent, right? So I would say 3 is equivalent to 6/2. Right? In fact, 3/1 is equal to 6/2, and a lot of the time we just say 3/1 is equal to 3. Right? But really, what we're trying to say is that they're equivalent. Okay, it's this different kind of relationship. Equals is kind of is asking a question sometimes if you put equals, but we're saying that they're equivalent. Okay, so 3 and 6/2 are equivalent. 0.5 and 1/2 are equivalent, right? So 0.5 is equivalent to 1/2, right? So these two things are written differently, but they mean the same thing. Okay, so that's important. So two things are equivalent. Two things are equivalent if they are written differently, but mean the same thing, right? What they're trying to describe is the same thing. Here, 3 and 6/2 are both trying to describe the number that comes after 2, right? That comes after 2 or is half of 6, right? Those are two ways to describe the same thing, or in other words, that place on the number line. They're both trying to describe that. In fact, these are all three things trying to describe the number 3, right? A symbol, a fraction, and a place on a number line. But we know what that thing is. It's the number 3, right? So, and same thing with 0.5 and 1/2. So functions are equivalent if they are written differently, but mean the same function. They represent the same function, okay? In other words, functions are equivalent, equivalent, if they are written differently, but have the exact same outputs for every input. So, for example, if f of 1 equals 3, and f of 2 equals 5, and f of 3 equals 7, right? And then g of 1 equals 3, and g of 2 equals 5, and g of 3 equals 7. So far, they are equivalent. So far, it looks like they are equivalent, right? So if I were to maybe graph this one, right, it'd be like, well, 1 and 3. So 3 might be there. So it might be something like that. That's just a guess of a sketch. And the other graph would be the exact same thing so far, right? So if they have the same outputs for every input, right? So for these inputs, input of 1, they both have an output of 3. Input of 2, they both have an output of 5. Input of 3, they both have an output of 7. So far they are equivalent. Testing points doesn't actually tell us if they're equivalent. It just gives us a hint, because f of 4 could be equal to 9, but g of 4 could be equal to 0. Right? We don't necessarily know that there's a pattern that's going to continue, right? But up to the third one, it looks like they're the same, right? So a notable thing is that equivalent functions that are equivalent have the same graph, okay? They have the same graph. And finally, let me kind of combine all the things here. So this was an important note. Let me have it here. I'll paste it there. Oh, not letting me paste. Okay, doesn't want me to. Sometimes it just doesn't like it when I try to paste things. There you go. Functions that are equivalent have the same graph. Functions are equivalent if they are written differently but have the exact same outputs for every input. And functions are equivalent if you can convert one into the other. For example, the two functions f of x equals, should I do the one that's on the screen here? Yes, I should. F of x equals x plus 1, x plus 2, and g of x equals x squared plus 3x plus 2. These are definitely written differently, right? Definitely written differently. Let's try to figure out if they're equivalent. So are they equivalent? So are these functions equivalent? Okay, so what we can check is, first of all, just choose some random input values and see if the outputs are the same. That's the first thing we'll do. Okay, graph each function and see if the graphs are the same. Okay, and the only way you can be 100% certain is try to convert one function into the other. Okay, so these are the 3 ways to check, are these two functions equivalent? So let's try to take a look. So first of all, choose some random input values and see if they're the same. So we're looking for, maybe I'll do what I said before. So f of 1, g of 1. Well, maybe I'll do g's after. So f of 1, f of 2. Oh, you might not be able to see, can you? You can barely see the top of the 2. So f of 2, f of 3. This will just give you an idea of if they're the same. If any of these don't match, they're definitely not equivalent. So this will just give you an idea of if they are equivalent or not. It will weed out all the functions that are definitely not equivalent. Right, so if they're definitely not equivalent, then you choose any 3 random ones, they probably won't match unless you're unlucky. But again, this will never give you actual concrete yes or no if they're equivalent. This is just an idea to get an idea. So f of 1, well, that's going to be 1 plus 1 times 1 plus 2, right? I'm just using the definition of f of x here. Okay, and so that's going to be, well, 1 plus 1 is 2 times 3, which is 6. Okay, 3 is 6. F of 2 is going to be 2 plus 1, 2 plus 2, which is going to be 3 times 4, which is 12. Okay, now that makes sense. Okay, so now f of 3 is going to be 3 plus 1, 3 plus 2, which is going to be 4 times 5, which is going to be 20. Let's compare now with g of x, right? So g of 1, g of 2, g of 3. And we're going to see if these outputs we get are going to be the same as f of x, as our function f. So let's start. G of 1 is going to be 1 squared plus 3 times 1 plus 2, right? So that's going to be 1 plus 3 plus 2, which is 6. Okay. So far, if we input 1 into either function, we get an output of 6 from either function. So that's confirming so far. That's a positive thing to say, yes, so far they are equivalent, at least for the value x equals 1, right? At least for that value, we know they're equivalent. We don't know they're equivalent for every x value, but we know they're equivalent for at least the x value of 1. Let's try 2. So 2 is going to be, g of 2 is going to be 2 squared plus 3 times 2 plus 2, which is going to be 4 plus 6 plus 2, which is going to be 12. So for x equals 2, we do f of 2, we get 12. G of 2, we also get 12. So far, the 2 functions are equivalent. Again, confirming so far that they are equivalent. Let's try g of 3. So 3 squared plus 3 times 2 plus, 3 times 3. Oops, made a mistake there. So 3 squared plus 3 times 3 plus 2 is going to be 9 plus 9 plus 2, which is 20. So f of 3 is equal to 20, g of 3 equals to 20. So far, that's giving us a good idea that these 2 functions are equivalent. Okay, but let's try to verify this even more. Let's look at the graph of both of these functions. How about that? So I'm going to go on Desmos and graph either of these functions. So our first one was f of x equals x plus 1, x plus 2. So that's what that function looks like, right? We can see a couple of the values we calculated, right? So f of a 1, we got 6, right? So if I try to draw the point 1, 6, you can see it's on the graph there, right? Because f of 1 is 6. That's why we have, at an x value of 1, we go up to 6 there, right? So f of 1 equals 6. F of 2 was 12, and so on. We could graph all of these. So there's our function f of x. And now let's look at g of x. G of x was x squared plus 3x plus 2. And would you look at that? The two functions perfectly overlap each other. Here, I'll make one dotted so you can see. One's dotted and one's the green line. So one's g of x is our purple dotted one here, and f of x is our green one. So if I just hide f of x, there's g of x, and there's f of x. And it looks like they perfectly overlap. So most of the time, this will be enough to say, yes, they are equivalent. But really, you are not sure that if you go all the way somewhere way out there, that one of these don't just start curving down. I mean, you have a pretty good idea. They're both quadratics, right? They're both quadratics. So they probably won't. But you don't know for certain until you actually show it with the last step. But anyways, for our second step here, right, this will give you a very solid guess as to whether they are equivalent or not, right? Especially in grade 11 functions, right? There's not going to be that many tricky questions they're going to throw at you, right? But it may seem like they are when they're not actually, until you zoom out more, right? Actually, I can give you an example of something like that where that might be true. So imagine this function here. Don't worry too much about what functions I'm writing here. So here's cos x, right? Here's cos x. Okay, so this is just a function that we're going to be talking about in chapter 5, I think. But again, don't worry too much about the function for now, right? And what about this function right here? I gotta go to another tab really quick. Sorry, I just decided to do this on the spot right here, so I gotta quickly look up just something I'm going to help understand what's happening here. So for cos x, there we go. So what about this function? Squared over 2 plus x to the 4 over 4. So again, don't worry too much about what I'm typing in there. Minus x to the 6. What I want you to look at is the graph. That's the point. X to the 6 over 6. Okay. So these two graphs, right? If I zoom in maybe one more, it might be a little helpful here. Maybe one little bit like that. Okay. So these two graphs here. This one is our cosine x. The other one I'll make is our dotted line here, right? It's our dotted line. So it looks like these two functions are equivalent, right? Because just by the graph of it, right? They perfectly match. They perfectly overlap. The blue one is our original graph and our original function, and our green one is our other function, the next one. So I'll say the first one is f of x equals cos x, right? And then g of x is our other one here, right? So you see that they do perfectly line up until you zoom out, and then they don't, right? So you see, just by looking at the graph, you don't actually know if you can zoom out to some point where it's going to be, they're not going to match anymore. Zooming way in, right? You can't even see at all that they start to separate. Zooming way in here, they look completely identical, right? But the more you zoom out, you can see that they in fact do not match. They only match between approximately here and here. So if you're interested in how I did this, and you're just if you're really curious about the math, this is some little bit later math, but you can look up a Taylor series if you're curious about how I did this, how I figured out how to do an example like this. Okay, so excuse me. So there's our kind of reasoning about why graphing doesn't actually give you the completely perfect answer. It doesn't give you the exact answer of yes or no. The only thing that gives you the only way to prove if two functions are equivalent is by using, so prove if two functions are equivalent by using this method. And that method is you convert one function into another algebraically. Okay, so let me write them again here. F of x equals x plus 1 x plus 2. And g of x is x squared plus 3x plus 2. Okay, so here, checking we're recording still, good. So here, I can turn one of these quadratics into another. I have to specifically look now, oh, these are quadratics. Okay, I see that these are quadratics. I can FOIL this, right? I can FOIL this, or I can factor this. So either I can convert this, hopefully, into that by foiling, or I can convert this into that by factoring. I'll go with the foiling method. It's a little bit simpler. So f of x is equal to, well, FOIL. So first is x times x, so x squared. Outer is x times 2, so 2x. Inner is 1 times x, so x. And last is 1 times 2, so 2. Okay, so f of x equals that. So that's equal to x squared plus 3x plus 2. And that's exactly what g of x is. So I've just proven now that f of x equals g of x. So I've proven it now. I've shown that these two things are equal. Okay, by showing that I can FOIL one and get the other. Or I could factor the g of x and get f of x by the same method. Okay, so that is the only way to prove that two functions are equivalent. And I would say it's best to go right for that method. If you think they might be and you don't want to put the work in, and maybe you just want to like see, okay, well, first I want to just check somehow if they're actually equivalent or not, instead of putting all the work in, well, graph them and take a look, and you can get a pretty solid guess as to whether or not they're equivalent. The only way to prove it is by actually doing something to the algebraic expressions here. Foiling, factoring, taking a common factor out, maybe dividing by something, multiplying by something, you can see that they'll be equivalent. Okay, so there is that. Is there anything else I wanted to mention quickly here? Nope, that's it. So that is everything for this topic. So equivalent functions is done. And now we move on to the main thing about this section. The next 2 points very nicely kind of move into lesson 9. Okay, so from everything now on is kind of combined with lesson 9. So if you feel confused about the end of this lesson, maybe watch lesson 9. Continue watching there. It's kind of like pretty much lesson 9 starts now, honestly. I don't really know exactly why the textbook decided to separate this way, but I've decided to stick with the textbook ordering just to keep some sort of structure instead of just making up my own structure, to help along with people who are following the textbook, of course. But yeah, so the ideas kind of from lesson 8 onwards, from this video onwards and into lesson 9 kind of jumble into the same thing. So we're talking about rational functions. So rational functions. Let's understand these words. Rational is anything that can be written as a ratio. A number that can be written as a ratio. Another word for ratio is fraction. So a number that can be written as a ratio. Not ration, or ration. It's a fraction. Okay, so rational numbers include 2/3, 1/2, 0.5. You know, that's not a written as a rational number, but it is a rational number, right? You can write it as a fraction because these two things are equal. A rational function is a function that is written as a fraction, right? So a rational function is a function that can be written as a ratio or fraction. Okay, so in a sense, right, every function could be written as a ratio. So like the function, you know, f of x equals 2x. Well, you could think of that as 2x over 1, right? So it's not too interesting to say that it's any function that can be written as a ratio. It's any function that has to be written as a ratio. So that has to be written as a ratio. Okay, so essentially the function 2x, or I'll say 2 over x, has to be written as a ratio. There's no other way to write that, right? 2 over x. So we see here that we have these fractions helping us along. So we essentially, the definition I'm going to put here is a rational function. Rational functions are functions with a variable in the denominator. Okay, a variable in the denominator. Okay. This kind of introduces where we're going into restrictions. Okay, so restrictions are going to come back right here, because that's why we mentioned them at the beginning of the lesson. So restrictions are going to come back right here. We start talking about rational functions. Remember when we started talking at the beginning of the lesson, one of my examples was 2x plus 1 over x. H of x equals 2x plus 1 over x. That's a rational function, because we have an x in the denominator. So we're going to keep talking about them here. So first of all, I'm going to look at a rational function. I'm going to give an example. I'm going to say h of x. Notice that, functions usually are h of x, g of x, f of x, g of x, h of x, p of x, q of x. What else have I seen? That's about it. Yeah, that's like, it could be anything. It doesn't really matter. I could say, that of x, and that would be a function. I just have to write that squiggle every time. But just so you're aware, most of the time, these are the symbols that are used. Okay, so F, G, and H, because those are on next to each other on the keyboard, and then P and Q, no particular reason. P usually for polynomial, and then Q comes after. So there you go. Okay, so just a quick side note, those are usually the symbols that are used. And you'll notice that that's what I've always been using. So h of x, let's take a look at this one here, is 3x squared plus 5x minus 1 over 2x plus 1. Okay, 2x plus 1. So we have a rational function here. Let's understand every part of this. A rational function, okay, so a rational function, rational functions can be written as, f of x equals p of x over q of x. So essentially, it's f of x, the rational function, so rational functions, which I'll call f of x, right, can be written as f of x, which is p of x over q of x, some polynomial over another polynomial. In fact, it doesn't even have to be polynomials, but that's usually that's the cases that we're going to talk about in this lesson, is going to be polynomial. So a polynomial over a polynomial, and that makes it a rational function. This is a polynomial, and that's a polynomial. So this right here, right, this is our p of x. Okay, that is our p of x. And this is our q of x. Okay. That is our q of x. So essentially, every rational function is just a function divided by a function. Right? P of x over q of x. And that together makes h of x, the fraction h of x. Okay? So of course, just a quick reminder, this is called the numerator. It's called the numerator. This is the denominator. I'm going to use these words a lot. So denominator. I'm going to use these words a lot. So I'm going to just remind you about what this is. And so the whole thing is called the rational function. Really quickly, okay, so I realized just that I I've used many times the symbol not equals, right? Like this, not equals. But I haven't actually ever defined that it is what that means. Maybe I've just mentioned it. So I'm going to use it a lot in this section. So I'm going to say that this means not equal. So it's essentially equal sign with a line through it. It means not equal. Okay, usually a line through it means not that thing, right? Okay, so the important thing about the rational functions, about every rational function, okay, is that it has a restriction. Okay, so every rational function, I'm going to write that right here, very important point. Every single rational function, has a restriction to, restriction to its domain, which is, maybe you can guess what it is. Q of x does not equal 0, right? Q of x can't equal 0. That's the restriction you're putting on the domain, because Q of x is our denominator function, right? That's the reason we give it names. We're kind of just giving it names here. P of x, Q of x. P of x is our numerator function. Q of x is our denominator function. So every rational function has a restriction to its domain, which is Q of x can't equal 0. So in this particular case, the domain of this, I know right away, is going to be, well, x can be any real number, but Q of x cannot equal 0. Okay. In fact, this right here, that's the domain of every single rational function. Okay. Is that the domain cannot be that unless there's anything extra funky going on, right? If P is a polynomial and Q is a polynomial, then this will be it. Q of X just can't be equal to 0. Okay, so then for this example, for this particular one, it's going to be the domain is, well, X is any real number such that 2x plus 1 does not equal 0. Okay, but 2x plus 1, well, we can actually simplify that a little bit. 2x plus 1 does not equal 0. What x value would make that 0? Essentially, we just solve for x here, right? So subtract 1 from both sides. Okay, subtract 1 from both sides. It's going to be 2x does not equal -1. Divide both sides by 2. Right, divide both sides by 2. X does not equal -1/2. And that is our final actual domain. Right, so let me just write it down here. The actual domain is the set x can be any real number such that x is not equal to -1/2. These are essentially equal, right? This and this are equal. It's just written a little nicer because 2x plus 1 doesn't equal 0. That doesn't exactly tell us what x value we're not allowing. This one does. We're exactly saying that the x value of -1/2 isn't allowed because that would make our denominator 0 if we put that in. If we use that as our x value, it would make our denominator 0. Okay, so essentially it's getting a little messy here, so I'm going to organize it quickly. So this is true here. I'll move it to the side. This is true for every rational function. Every rational function has a restriction to its domain, which is that. And so the domain of every rational function, every standard simple rational function, is x can be any real number, but the denominator cannot be equal to 0. And you want to actually solve for what x value makes it 0. Okay. Okay. So there we go. That looks like, so look at domain and range, show the domain just by, that's fine. The range is essentially going to be any real number, but I think it'll always be any real number. That's not true, actually. So I can't say that. The range, you're going to have to look at the graph to understand what the range is. Okay, so we're going to, actually, let's look at some examples now. Let's talk about the range of rational functions, okay? And I guess that'll bring us into the graph. So range plus graphs of rational functions. Okay, that's going to be kind of our next one. Actually, I didn't even intend to talk about that in this lesson, but I think it's important. So let's actually do it. So let's look at this example that I wrote right here. H of x equals this right here. So 3x squared plus 5x minus 1. Actually, it's written right here next to me, so I should just look there. Over 2x plus 1. And then I'm also going to look at another one, g of x, another function, g of x, which is 1 over x squared. Okay. So we're going to look at these two functions, and we're going to first of all look at their graphs, because they're going to be, you've never seen graphs of rational functions before. Okay. Let's see. I think in this, okay, let's see what the graphs, and then I'll think about where I want to go after this. This lesson has a few, improvised, I guess, sections. I mean, all of it's kind of improvised, but unplanned sections to it, which I just think are good additions. So first of all, our function here, 3x squared plus 5x minus 1. Oops. Sorry, gotta scroll down. I clicked a button wrong here. Scroll for a bunch of time. Okay, there we go. So the fraction 3x squared plus 5x minus 1 and 2x plus 1. Okay, so this is our rational function. This is our rational function like this. You can zoom out a little bit. You'll see it goes kind of forever in that direction, this direction, right? Maybe you'll notice that it seems like it's getting closer and closer to the y-axis here, right? But it's kind of just staying kind of vertical like that. So it's here it passes through the x-axis, here it passes through the x-axis, has this kind of like bendy shape. So these two lines never touch here. So, okay. It is a function because it passes the vertical line test, right? I can draw a vertical line anywhere, and it doesn't cross. So you may be wondering, what about like in this section here, right? If I vary this. So there's our vertical line that I'm drawing. How about I make it a dotted line, right? Does it actually pass the vertical line test? Maybe someone, some of you are wondering. It does, because you see here, well, it's passing once, passing once, passing once. Here it's still passing once. Here it's still passing once down here, right? It's passing once right there. Here it's still passing once, and then here it's passing once, but up there, up top here, right? Now it's crossing through up here. Right? So it's always passing once, and then not down there anymore, and up here. So it's always passing through the graph once. Okay, it might look like there's two graphs here, but it's really the same graph. It's just kind of disconnected. There's a disconnect between the two parts of it. So this is a part of the graph, and that's another part. So there's, exactly. It's discontinuous is the word you probably use for that. So there's our graph of that one. Now the range is another question, right? Maybe I'll take a quick screenshot of this to help us out here. So the range of this function is all the possible outputs we get from the function, right? All the possible outputs. So do we get any of these numbers as outputs? Yeah, we do, right? From actually two different possibilities. From here, you know, maybe like this output right here. Well, we get it from whatever x value that is, and we also get it from whatever x value that is, right? We get that height there. And so this is in the range, this section going up to infinity. This section's also in the range. So our range is all real numbers, right? The graph kind of paints the whole y-axis. So our range is all real numbers. So range is the set. All the y values can be any real number, and that's it. Y can be any real number. Now, g of x is a little bit different, right? So if I write g of x equals 1 over x squared, it looks like this, right? Similar kind of thing. We have two parts. See, it's a similar thing where we have two different parts to the graph, and they don't meet up here. Importantly, they might look like they're going to meet, but they don't. See, like up here, maybe you're saying, oh, well, they meet right there, right? They're meeting here. But if I zoom in, they don't meet, right? And actually, I'm going to tell you right now, it doesn't matter how high we go, they will never meet. Right? So I can go way, way up here, right? And then try to zoom in. They look like they meet, right? And then just I have to zoom in far enough, and you'll see that they don't meet, in fact. So let's take a graph. Let's take a screenshot, of this graph, right? So our graph of our function is that right there. Now, what's the range of this function? Well, let's just take a guess here. Well, what about this? 2. Is 2 in the range? Well, yeah, because 2 can be is the output when you take in this x value, whatever x value that is, right? We go, well, not a straight line. Whatever x value that is right there, we get 2 as an output, and also whatever x value it is here. So we get 2 as an output for either of these values, either of these x values. So yes, 2 is in the range. Similar reasoning can be done for any positive number, right? 0 now. Do we ever get 0? That's actually a really, really interesting question, really important question, is to say, well, we would get 0 if either of these legs ever touch the x-axis. Either of these legs ever touch the x-axis coming down like that. You see how they get closer and closer, right? They're kind of squeezing in on the x-axis. So let's see, do these legs ever touch the x-axis? They definitely look like they do. But again, if I zoom in, they don't touch the x-axis. That's the x-axis there. That's the graph. And hopefully you can believe me. If you don't believe me, graph this yourself and take a look. Doesn't matter how far you go in either direction, it'll never touch the x-axis. So 0 is not in the range. And similarly, no negative numbers in the range. We never get a negative number as an output. So, right, so that's this whole section. This whole section, not in the range, not in the range. So the range is just that blue section there. Our range is the set of y values, which can be any real number, with a restriction that the y value has to be greater than 0. And also not greater or equal to 0. It can't be equal to 0. It has to be greater than 0. Specifically greater. Not greater or equal to. Specifically greater. And there's the range of our function. So these ones you kind of have to actually look at to understand what the range is. It's a little bit hard to just find it from the equation. So yeah, it's important to look at it here. Okay, there we have it. That is our range and the graphs of rational functions. We're going to talk a lot about the graphs of rational functions when we get to a chapter where we're more talking about transformations and things like that. But yeah, so that's about all. Maybe you're asking yourself, why does it make this kind of curvy shape like that? And we're gonna definitely talk about that. Just not quite in this lesson right here. Okay, you know what? Actually, we're going to do it today. We're going to talk about why do rational functions look like this today. It's going to be just a quick side note, essentially, here that isn't directly related to any other content in the section. But since you're learning about a whole new type of function, it's good to know why does it look like this, right? So like the parabola, we just, we understood why it looked like that, because as you square things, it gets faster, bigger and bigger distances between the squares. So we're going to start curving upwards, right? Lines go up by the same amount each time. So that's why it looks like a line. But why do we get, for example, I'm going to start with the most basic rational function you can have, f of x equals 1 over x. And we're going to understand why this function looks like that. And then from there, we're going to, we can kind of use logic from that to understand any rational function or any simple rational function. Let's start by plotting some points. Let's do a hand-done graph here. So f of -2, actually, well, to do a graph, we're going to usually make a table of values first. So f of x and x here. So I'm going to choose some x values, -3, -2, -1, 0, 1, 2, 3, right? So let's take a look here. F of -3, so f of -3 is going to be -1/3. F of -2 is going to be -1/2, right? F of -1 is going to be -1. F of 0 is, F of 0 is not in the domain, right? It's just f of 0 is question mark, question mark, question mark, because f of 0 is not in the domain of this function. We cannot put in 0 into this, right? Okay, f of 1 is 1, f of 2 is 1/2, and f of 3 is 1/3. So I'm going to start plotting all these points here. Let's say 1's right there, 2, 3, 4, 5, 1, 2, 3. We don't only need that much, it's fine. So I'll say this is 1. Yeah, I'll say that's 1 there. Okay, so here we have f of -3, which would be right here. -3 is right here. Was -1/3. Right, so that's kind of going to be something here. That's -1. That's 1. So f of -3 is going to be -1/3. So it's going to be about right there, right? F of -2 is -1/2. So that's going to be something like right there. F of -1 was 1, or sorry, was -1. It's going to look like that. And then f of 0, we don't know what that is, right? It doesn't really, nothing happens there, right? We're not in the domain. F of 1, though, was 1. So we have a point there. F of 2 was 1/2. F of 3 was 1/3. So you see, we kind of have this similar kind of curvy shape on either side going there, right? So if I graph this, if I graph it with Desmos, we'll see a more accurate picture. But what I want to kind of, take a look at is, what about numbers between 0 and 1, right? Or so what if I did f of, here's our number line, right? There's 0, there's 1. So what if I did f of 1/4, 1/2, and 3/4? So 0.25, 0.5, 0.75. So f of 0 was question mark, question mark, question mark. F of 0.25 would be 1 over 0.25, which would be 4. F of 0.5, f of 0.5 would be 1 over 0.5, which would be 2. Which would be 2. And f of 0.75 would be, 4/3, right? So 4 over 3. So I should say 1 over 0.75, which would be 4 over 3. Okay, so we can see here, right, these are the numbers. Now what's happening here? As x gets bigger, the f of x gets smaller, right? X is getting bigger here. F of x getting smaller. So essentially we're going like that kind of, right? So, f of 0.25, 0.25 would be like right there maybe, right? 0.25 was 4, so that'd be like way up here somewhere. Way up there, literally, right there. F of 0.5 was 2, so that would be about right there. So 0.5 is right there, so maybe 2 would be like right there, right? F of 0.75 was 4/3, so that would be maybe something like right there. 4/3 is right there, so we go like that. And you can see we kind of shoot up right after we go less than 1. We shoot up really quickly. And that's because we're dividing by a decimal number, right? What about f of 0.1? That would be 1 over 0.1. That's 10. What about f of 0.01? That's 1 over 0.01. That's 100. So as the input gets smaller and smaller and smaller, as the input gets closer and closer to 0, our output is shooting up really, really far. right? So f of 0.00001, that'll be 1 over 0.00001. That's tens, hundreds, thousands, 10,000, 100,000. So that would be 100,000, like that. And so we can see if we were to graph this function, f of x equals 1 over x, as we get closer and closer to the y-axis, right, as our x value, right, so as x equals, I should say x equals 3, as the x value gets closer and closer to the y-axis, right, the output value shoots up farther and farther and farther. And as we get closer to the y-axis, our x value gets closer and closer to 0, our value goes higher and higher and higher, right? And so you may say, well, what if we, actually got as close as possible to 0, right? Well, we'd kind of go to infinity, right? Our y value would go to infinity here. The output from our function would go up to infinity, right? So, but then on the actual number 0, it's undefined. It would be 1 over 0. 1 over a little tiny number is a huge number, but 1 over 0 is not infinity. It's just we don't know what it is, right? It's just not a number. Sorry, I shouldn't say we don't know what it is. It's just not a number, right? So we see here that that's what's happening. That's why the graph looks like this. And as we get bigger, as our x value gets bigger, well, our height is just going to be a smaller and smaller fraction. 1 over 4, 1 over 5, 1 over 6, 1 over 29, 1 over 30. As you go further and further, 1 over 58. But is that ever going to equal 0? Can you ever take 1 and split it up into a way that each thing gets 0 parts of 1? Right? 1 divided by anything will never give you 0. 1 over 85, 1 over 98, 1 over 115. As we keep going, it's going to be 1 over 1,360. As you can see, doesn't matter how far. 1 over 3,000, 1 over 100, 1 over 300. Oh my God. As you can see, as far as we go, 1 over 1,360 is still not 0. It's a tiny number, but still not 0, right? It's a tiny height. And so no matter what, this leg, I like to call it, this kind of leg of the graph, will never touch the x-axis. Just like this kind of spike of the graph will never touch the y-axis. And for the exact same reasoning, this side is just going to be negative because you're putting in negative x values, right? So it's going to be below the x-axis. All the y values are going to be negative. Exact same reasoning though. This leg never touches the x-axis, and this leg never touches the y-axis. So hopefully that made sense. If that didn't make too much sense, watch it again. This takes some, a little bit of digesting here, right? But the important facts to remember are that 1 over anything will never equal 0. Never equal 0. So that's why this is why the legs never touch. So legs of the graph never touch the x-axis. Okay. And 1 over a small number, it gets closer and closer to infinity, right? It gets closer and closer to infinity. Well, that's kind of a bad way to say it, but it gets bigger and bigger. The number gets bigger and bigger the smaller this number is, right? So that's why the spikes shoot up as very high. So this is why the spikes shoot up high near x equals 0. But actual x equals 0, right? 1 over 0 does not exist. 1 over 0 does not exist. Does not exist. There's names for this kind of behavior. Okay, there's names for this, and it's called an asymptote. So asymptote is spelled like that, right? So an asymptote is what you're seeing here. It's the idea that some part of a function is getting closer and closer. It's approaching a y value of 0, right? We're getting closer and closer to 0, but we'll never touch 0 because we're always going to be 1 divided by something, and that will never be 0. Right? So we're getting closer and closer to 0, but we're never actually going to equal 0, our height. And here, our height is going up to infinity, and our x value is getting closer and closer to 0, but our x value will never actually equal 0. Right? because 1 over 0 is not a number that exists. Okay, there's our little bit of a side story about why the graphs look like this. This wasn't actually covered in the textbook at this point, but I don't see why not. This is a good, we're introducing rational functions, so this is the best time to talk about why the graphs look like this. Right? But yeah, that's the idea. Okay, so there is that. Let's take a look at what's everything that I talked about here. So rational functions are, I should say functions, plural, so rational functions are done essentially. Let's just make sure. I'm going to make sure that we have everything worked out there. Good. Yep, that's totally good with me. So now we're going to just talk a little bit about rational functions being equivalent to simpler functions or polynomials. Okay, so rational functions can be equivalent to other things. So first of all, I'm just going to remind you, right, that so maybe I'll make the title first. So rational functions can be equivalent to other functions. Okay, so I'm going to remind you quickly, 4 over 8, we can simplify this fraction by taking out a common factor. So essentially what we do is we write 4 over 8 as 2 times 2 over 2 times 4. And we notice here that we're multiplying by 2 on the top and bottom. So I could write this as 2 over 2 times 2 over 4. Right? And yeah, and that's not what I meant to do. So we can simplify the fraction 4 over 8 by writing 4 over 8 as 4 times 1 over 4 times 2, right? And this lets us cancel the 4 and the 4 because we have a 4 on the numerator and 4 on the denominator, and we can just write this as 1/2. So 4 over 8 is equal to 1/2 for this reason. Okay, and we're going to do a very, very similar thing here, right? We're going to do a very, very similar thing, but it's important to understand why you're allowed to do this, right? Why are we allowed to just simplify like this? Or why are we even allowed to just say, well, divide this by 4, divide this by 4, and that'll give you the same answer. That'll jump you right here, right? Maybe this is how most of you do it. So you're allowed to divide by 4 because you're taking out a factor of 4. Essentially, you're doing this, right? You're taking out this 4, so it's essentially dividing 4 by 4, you get 1, so it's 4 times 1. And 8 divided by 4 is 2, so 4 times 2 is 8. But why are we allowed to cancel? The reason we're allowed to cancel is because what you're really doing, and you usually don't write this, but the reason you're allowed to do it is because what you're really doing is you're turning 4 times 1 over 4 times 2 into 4 times 4 over 1 over 2. Sorry, 4 times 4 times 1 over 2. 4 over 4, that's 1. And so 1 times 1/2 is just 1/2. And that's why we're allowed to cancel. Because what you're doing is you're multiplying the top and you're multiplying by the bottom, by the same number. That's the same thing as just multiplying by 1. Right? It's the same thing because it's just multiplying by 4 over 4, which is 1. So it's important to understand this because that's how we're going to be treating it in this section right here. That's how we're going to be dealing with these kind of things. Okay, so just like how in this fraction here, we can cancel out the 4 and the 4, which is how the simplification works. And again, like I just explained, is that's done by the fact that we're really just multiplying by 1 here. When we work with rational functions, we're going to have the exact same property. So if I look at, for example, the function f of x equals x plus 1, or I don't have to put brackets, x plus 1 over x plus 1, right? Let's take a look at some values here. So f of 1 maybe, f of 0, f of 2, and let's take a look at all these things. So, and then I guess finally actually f of -1. So f of 1 would be 1 plus 1 over 1 plus 1, which would be 2 over 2, which would be 1, right? 2 over 2 is 1. Similarly, f of 0 would be 0 plus 1 over 0 plus 1, which would be 1 over 1, which is 1. F of 2 would be 2 plus 1 over 2 plus 1, which would be 3 over 3, which is 1. So it looks like we're getting 1 out of everything. But what if I put in -1? That would be -1 plus 1 over -1 plus 1. that would be 0 over 0. Well, here we have a problem. 0 over 0 is not a number, right? So I'm going to say here, not a number. And that comes from the fact that the domain of this function right here, right? The domain of that function, remember, is, so the domain is going to be, well, the set of all values x, which can be any real numbers, but the denominator can't be equal to 0. X plus 1 cannot be equal to 0. Or in other words, x plus 1 not equal to 0 is the same thing as saying, well, subtract, isolate x here. It's going to be move that plus 1 to the other side. X cannot equal negative 1. Right? So the domain is the set of all x values such that x does not equal negative 1. These two sets, these two sets are the same. So maybe I'll just show the line here, the process of how to get that. So you see, plugging in negative 1 doesn't make sense. So f of x, we can almost say that f of x, which is x plus 1 over x plus 1, is equal to 1. Right? So we could say f of x equals 1 here. That would almost be true. Because like for this function here, f of, or maybe I'll say g of x. G of x like that. G of x is 1. So if I take a look at g of 1, g of 0, g of 2, and g of negative 1, right? We're going to get all the same answers. G of 1 is 1. There's no x here, so all the answers are going to be 1. G of 0 is 1. G of 2 is 1. G of negative 1 is 1. So essentially, all of these, by checking all these points, we've been on the right track that f of x is equivalent to g of x, right? And even if I graph them, right, if I take a graph here and I graph f of x first, so f of x is the fraction x plus 1 over x plus 1. You can see here we have a flat line, and if I graph the function g of x equals 1, we also just have a flat line, right? All the heights are 1 here. But there is a difference. On f of x, our x value cannot be negative 1, right? Our x value cannot be negative 1. So if I look right here, you see, if I try to find where x is negative 1, and I look at what Desmos is telling me, negative 1 has a height undefined. Undefined. That means, because we would get 0 over 0, right, with that. That's what I showed right here. We get 0 over 0 if I do f of negative 1. So there's a hole there. We call that a hole. And we draw it with that little circle, like a little circle, empty circle. So as you can see, hopefully you can zoom in, you can see the little circle there. Can I draw it any bigger? No, it doesn't look like I can. But here, how about I just draw the point in? So it would be negative 1, 1. I want to draw it as a... There we go. So that's kind of what it looks like there, right? So you see on this graph, we have a hole at x equals negative 1. That one spot is not in the domain of this function. So you have a hole there. But g of x does not have this problem. G of x equals 1 does have a value when x is negative 1, and that's 1. So you see, f of x and g of x are not exactly equivalent, because look, f of negative 1 is not a number. G of negative 1 is 1. But if I write g of x as 1 with a little side note here, kind of you think of it as like, oh no, side note, it's 1, but x cannot equal negative 1, then this is equivalent to f of x. This is equivalent. Actually, I'll use the words is equivalent to. I'll say is equivalent to f of x. Or in other words, g of x, or actually, I'll just write it here. F of x equals x plus 1 over x plus 1. These are equivalent. In comparison, g of x equals 1 is not equivalent to f of x equals x plus 1 over x plus 1. So these are equivalent, these are not. And you see, what the difference is that I'm adding the restriction here in words. This is the restriction. Here, I'm putting a comma and then saying the restriction outright there. And that's kind of how you do it. You can say these two are equivalent because g of x equals 1 such that x cannot equal negative 1 is completely equivalent to f of x equals x plus 1 over x plus 1. Because both of these will always evaluate to 1 whenever you put an x value that's in its domain. Right? as we saw here, f always evaluated to 1, g always evaluated to 1, but neither of them should evaluate to anything when x equals negative 1, because f of x is a number, f of negative 1 is a number that doesn't exist, so g of negative 1 should also be a number that doesn't exist. So in this case it is, if I say 1 such that x cannot equal negative 1. So we can see here that our function f of x was always equivalent to 1 such that x cannot equal negative 1. This rational function simplified to just a constant function, just a number. It's a function that always outputs 1. Let's look at a couple more examples here. Okay, let's look at a couple more examples. So if I have another function, it's going to be a different example. I'll say f of x equals x plus 2 x plus 1 over x plus 2 x plus 3. I want to see what function this is equivalent to. Well, I'm going to notice something here, that I have a factor of x plus 2 and x plus 2 on the numerator and the denominator. So just like when I had 2 times 2 over 2 times 3, I could cancel out the 2's, I could cancel out these guys too. Right? I could cancel out the x plus 2 and the x plus 2. But I have to take into account the fact that we started with some restrictions here. We started with that the denominator cannot equal 0. I can't forget about that. So the restrictions that I have are x plus 2, x plus 3 cannot equal 0. Or in other words, if we have two things multiplying together and they're equaling 0, then the first thing, either the first thing equals 0 or the second thing equals 0, exactly like when we were solving quadratics. So you can kind of think of it as each factor. You can just pull out each factor here. X cannot equal negative 2, x cannot equal negative 3. And we have two restrictions on this function. So this is equal to, well, if I just cancel out these guys like that, this is equal to x plus 1, x plus 3, but with the restriction that x cannot equal negative 2 and x cannot equal negative 3. And even though now, in this, I could plug in negative 2, right? Here I could not plug in negative 2, because here, if I just look at f, our original f of x, which was x plus 2 over x plus 1, x plus 2, x plus 1 over x plus 2, x plus 3, and I took f of negative 2, well, that would be negative 2 plus 2, negative 2 plus 1 over negative 2 plus 2, negative 2 plus 3, that's 0 over 0, which is a number that doesn't exist. Negative 2 plus 2 is 0. So it would be 0 times that over 0 times that. It'd be 0 over 0, a number that doesn't exist. But this function here, right, if I didn't put the restriction, if I didn't put this restriction here, right, imagine that wasn't there for a second, I could evaluate this. I could define a new function, g of x, which is x plus 1 over x plus 3, right? Still, x can't be negative 3 because that denominator would be not the number we want. We would get a 0 on the denominator there. But I could evaluate g of negative 2. Negative 2 plus 1 over negative 2 plus 3. That would be negative 2 plus 1 is negative 1. Negative 2 plus 3 is 1. So that would be negative 1. And g of negative 2 exists. But g of x is not equivalent to f of x unless I put the restriction on. And now, x cannot equal negative 3. Now they are equivalent. So if I don't put the restriction, just simplifying, you don't get a function that's equivalent. So that's the main takeaway from what I've been talking about here, right? So simplifying rational functions by just canceling common terms between the numerator and denominator is not enough to get a equivalent function. You must also write down the restrictions. Okay, the restrictions that the original function had. Restrictions that the original function. Okay, so you must write that down. So you see the original function had a restriction that x couldn't be -2 and x couldn't be -3. So any equivalent function has to also have those restrictions. Okay, they have to also have those restrictions. So f of x is equal to x plus 2 over x plus 2, x plus 1 over x plus 2, x plus 3 by canceling, right? That is equal to x plus 1 over x plus 3, but you need to explicitly write the condition that x cannot equal -2. And from this, we can also see separately that x cannot equal -3 from the fact that this denominator can't be 0 either. So we get that from that, but we get that from our cancellation. Right? We get that from our cancellation. This restriction comes from the cancellation. This restriction just comes from the fact that we still have an x plus 3 in the denominator. Right? Which tells us that x cannot equal -3, because if it did, that would be -3 plus 3. That would be 0 in the denominator. Okay. So essentially, if you don't account for the restrictions, they're almost equivalent. They're not exactly equivalent. They're almost equivalent. But when you do account for the restrictions, they are exactly equivalent. Okay? When you do actually write them there. Let's do one more example, and then I'm going to go through like a whole process with you. So essentially, we have the rest of the lesson is going to be 4 more examples of this. So the last example before I go through the actual process that I've worked out is this example. So find an equivalent function to this f of x, which is x squared plus 3x plus 2 over x plus 2. Okay, so you see on the top we have a quadratic, and on the bottom we have a linear function, right? This is our p of x, q of x. Top is quadratic, bottom is linear. So what I'm going to do is I'm going to factor the top to see if I can cancel with x plus 2 on the bottom. So I'm going to factor, just get it in a different form. So essentially I have to factor x squared plus 3x plus 2. I can do this in lots of ways. We went through a whole lesson on how to do this, but I guess factoring, we have one method to factor, but solving this, we have lots of ways. So to factor it, I need to find 2 numbers that add to 3, but multiply to 2. So how can we get 2? Well, 2 we can get from 1 times 2, and that will be the answer. So the numerator is x plus 1, x plus 2, and the denominator is x plus 2. Well, look at that. We can cancel an x plus 2 with an x plus 2. And if I write this here, right, this is equal to x plus 1 over 1, right? Because we just have a 1 on the bottom here, or just x plus 1. But we are not quite equal yet. We have to, I guess those 2 things are equal, but this is not quite equal to that. Because we have to account for the restrictions. This function had restrictions that x, the denominator can never be 0. In other words, x plus 2 cannot equal 0. Or in other words, x cannot equal -2, just by solving for x here. Just treat this like an equal sign and solve for x. Right? X cannot equal -2. So here, x can also not equal -2. And officially, this is equal to f of x. X plus 1, but x can just not be -2. That is equal to this whole complicated thing, right? This whole complicated thing can simplify to just x plus 1. But you have a restriction there. That's the important thing. You have a restriction. So if I look at the graph of f of x, we're going to see it's just x plus 1. But we have a hole there. So if I look at f of x, which was x squared plus, plus 3x plus 2 over x plus 2, you see that's completely the same as the line x plus 1. Right? These two are the same thing essentially. Right? So my dotted line will be our x plus 1. So that blue dotted line is our x plus 1. Right? But the difference is that f of x, it has a hole. There's a hole at the point, where x equals -2. Right? When x is -2, at the point -2, -1, yeah, right there. So you see right here, we have a hole on our f of x. So I trace f of x here, see how Desmos gives me x, y values, and then if I go to -2, it's undefined. Right? There is no f of -2, but only -2. And where does that come from? From the fact that if I put -2 into the function, right, I would have a denominator of 0. -2 plus 2 would be 0. And so I would not be able to calculate that. So there is no f of -2. Otherwise, it's the same as x plus 1. And we showed that by just canceling out factors. And we see all we have left is x plus 1. Okay, so let's take a look now at a general method to simplify a rational function. So this is the general method to simplify a rational function. We're going to go through 3 examples of this. So first of all, begin with, if we have some function f of x equals p of x over q of x, right? That's every rational function is in this form. So the first step number 1, is to factor p of x, and factor q of x. So let's go through this process with an example. Our beginning function here, so I'll write the example in purple and the steps in black. So the beginning function is f of x equals x squared plus 4x plus 3 over x plus 1. So step number 1 is factor both of them. Well, our denominator is already factored, right? Our numerator now has to be factored. X squared plus 4x plus 3. Well, we're looking for, just on the side here quickly, there's 2 numbers that add to 4, but multiply to 3. Right? Well, how do we multiply to 3? We do 1 times 3, so 1 and 3 are our answers. So our numerator is x plus 1, x plus 3. So you see how factoring is a really useful skill that you need for this course, right? We're using it all the time. And so now I factored it. Okay, step number 2 is going to be, now is a good time to note down the restrictions. I'm really having trouble spelling restrictions. Restrictions by setting q of x equal to 0. Right? And solving for x. Right? So we're taking the denominator, x plus 1, setting q of x equal to 0, but we want to not equal 0. That's why I put the not here, right? And we want to just solve for x here. So x cannot equal -1. There we go. There is our step number 2. I'm going to just make that purple because that's the example, right? So there's our restriction noted down. Okay. Step 3 is essentially cancel out any common factors that appear in the factored p of x and factored q of x, right? So I'm going to just write down the factored form again right here of our example. So I'm going to go like that. Cancel out any common factors. Yeah, we have common factors, x plus 1 and x plus 1. Right? And so the remaining factors, whatever's left, is your simplified form. So just like write out the remaining, step 4, I guess, is write out the remaining function with restrictions. Okay, so the final form is that this is still f of x, right? As long as we keep this going, we're still equal to f of x here. This is going to be x plus 3 with the restriction that x cannot equal -1. This restriction comes down there. And so f of x is x plus 3 such that x cannot equal -1 is the same thing as f of x. This complicated looking quadratic divided by a linear function is the same thing as x plus 3, just that x cannot equal -1. So let's graph that here. So if I graph, first of all, am I in the big? Yeah. First of all, I'm going to graph our original function f of x, which was x squared plus 4x plus 3 over x plus 1. Okay, so that is our function. Notice that everything's good except when x equals -1. And then we have a hole there. It's undefined. You see how Desmos says undefined? Because f of -1 just doesn't exist, because you'd have a 0 on the denominator. So -1, 2, I'm quite certain. Yeah, there you go. -1, 2 is our hole. So I'm just going to add that in there. You see that's the hole. And you see that this line is the same thing as the line x plus 3. Right? There's our line x plus 3. The only difference is that x plus 3 doesn't have a hole at -1, at x equals -1. Our function does. Right? Our function does. So that's the difference there. Okay, so there is our function, and there's our original form, and there's our simplified form. Let's go through this process with 2 more examples. So again, step number 1, I'll just type it this time. So step number 1 is factor both the numerator and denominator. So I should have written the example first, sorry. So f of x, our example is f of x equals x squared plus 3x minus 10 over x squared minus 2x. Okay. So now, step number 1 is factor both the numerator and the denominator. So our new function f of x is going to be the factored numerator. So I'm looking for 2 numbers that add to 3 and multiply to -10. Okay, well, how do we get -10? Well, 1 times 10, no, 5 times 2. I'm going to say 2 times 5. That's almost 10, but I want to get 3. So 5 minus 2 would give me 3, and 5 times -2 would give me -10. So the answer is -2 and 5. When I add them, I get 3. When I multiply them, I get -10. So the numerator is x minus 2, x plus 5, and the denominator, well, we got to factor this. Here we don't have to do anything fancy. I can just common factor out an x. Common factor out an x, so what's left? X minus 2. Just divide everything by x here, and we get x times x minus 2. You can distribute this back in if you want to see that that's equal to our original denominator. Okay, so I successfully factored our denominator here. Now, our step number 2 is note down any restrictions. Restrictions, that's an important thing. So note down any restrictions. We're going to have, well, the denominator has 2 possible restrictions, right? We do this by taking the denominator, x minus 2, and saying, well, we don't want this to equal 0. So how could it equal 0? Well, either the first thing, x could equal 0, or x minus 2 could equal 0, right? In other words, x not equal to 2. So those are our 2 restrictions. X can't be 0 and x can't be 2. Because if it was, then our denominator would turn to 0. We'd have 0 times something, or something times 0. Either way, we'd have a 0 in our denominator, and we don't want that. The 2 ways that can happen is if x is 0 and x is 2. So there's our restrictions. Okay, and then step number 3 is going to be cancel any common terms, right? So we can do that here if I just copy the function over. Cancel any common terms. We have OneNote's being weird, as always. Thanks. We can cancel x minus 2 with x minus 2, and we're left with step number 4, which is just write out the remaining factors, or the remaining factors in the function, with restriction, right? With the restrictions that we put on, which is going to be f of x equals x plus 5 over x, but x cannot equal 0 and x cannot equal 2. Those are our restrictions there. And so there we have it. That is our function. So if I look at the graph of either of these functions, f of x is, so it's equal to x squared plus x squared plus 3x minus 10 over x squared minus 2x, right? We see that we have this function, which is the same as some other function, g of x, which would be x, what was it? What did we simplify it to? X plus 5 over x. So x plus 5 over x. You see that these are the same functions. The only difference is that x plus 5 over x doesn't have the same holes, right? So x, this original function, has a hole at 0, which is fine. That's exactly where we have our discontinuity in both cases here, where the kind of the graph separates into two separate pieces at 0. Both of them have that because g of x also can't have x equal to 0. But g of x doesn't have a hole at 2, while our original function f of x does. So at 2, you can see it here. Where is it? There you go. 2, we have an undefined point on f of x, but not on g of x. So that's why you have to explicitly write in the restrictions, because otherwise they're not there. Okay, there's that. Let's do one more example and that'll finish up the lesson. I know it's a long lesson, so hopefully you're sticking through. So final example is if we have f of x equal to x squared plus x minus 2 over x squared plus 5x minus 6. So see if you can follow along with the steps here. First step is factor. I'm not going to write the steps how I usually do, so I'm going to just try to write like this, like we're solving it together. So factor is our first step. Factor the numerator. Well, I want two numbers that add to 1 and multiply to negative 2. How do you multiply to negative 2? You can have, well, 1 times 2. And, well, 2 minus 1 is 1. So negative 1 times 2 is negative 2. And that is our two numbers there. So the numerator is x minus 1, x plus 2. And our denominator, so that was for the numerator here. Let me just box that in like that. That was for the numerator. And now for the denominator, we need two numbers that add to 5 and multiply to negative 6. So we can do that by, well, 1 times 6. 1 minus 6 is negative 5, but 6 minus 1 is 5. So negative 1 and 6, negative 1 and 6, multiply to negative 6. So these two are for our denominator. Our denominator factors into x minus 1, x plus 6. Next, we can cancel whatever we want to cancel, whatever we can cancel, and we're left with x plus 2 over x plus 6, but we have to incorporate the restrictions. So what were the restrictions on this original one here? Well, our restrictions were that x minus 1 cannot equal 0, first factor. And the other restriction is that x plus 6 cannot equal 0. So what actual x values is that? Well, x cannot equal 1, and x cannot equal negative 6. And those are the exact restrictions that we want to put here. X cannot equal 1, and x cannot equal negative 6. And there we have it. This function right here, this simple, much simpler rational function with two restrictions, is the same thing as this complicated rational function with no restrictions. Right? So these are equivalent. This is still f of x here. It's the same thing as f of x because I included these restrictions. If the restrictions weren't there, this would not be f of x. But since the restrictions are there, that is the same thing as f of x. Just simplified. So the whole point was to simplify. Okay, well, that is everything for this lesson here. That's all the examples I wanted to go through, and we got through all the stuff. So this is a pretty long lesson today. My recording is now 1 hour and 51 minutes, but a lot of stuff is going to be cut out. Anyways, let's do a just quick review of what everything was that we talked about here. I guess I can go right to the top. I don't have to do the whole typing thing because I typed it at the start here. So we reviewed domain. We talked about restrictions, what restrictions are to a domain. We talked about how certain functions can be equivalent. We introduced rational functions and talked about why the graphs of rational functions look like the way they do. And then we talked about simplifying rational functions. And that was the last thing we talked about. And so if you want more information about why this stuff works at the end here, how other things we can do with rational functions, that kind of goes along with this kind of idea here of simplifying them, we're going to talk a lot about that in the next lesson, okay, which is going to be working with rational expressions in lesson 9. So yeah. Okay, well, that's everything for this lesson. If you have any questions, you can email me, as always, at second teacher program at gmail.com, or you can also book a session by going to the information page for this course. So www. Actually, no, I'll just say book a session. Book a session. There you go. Okay, well, thank you so much for watching. I hope it was helpful, and have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.